This is Dr. D. Govardhan, Professor and Dean, Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today, I am covering the topic thin cylinders in Mechanics of Solids for the third semester. Here, the thin cylinders are generally classified into two types. Thin cylinders and thick cylinders. These are having many engineering applications, such as for transporting or storage of liquids, gases, as well as the fluids. Examples, we are taking the pipes, boilers, storage tanks, etc. These are, when they are stored that fluids in it, they are subjected to certain fluid pressure, even though it is storage or transporting the fluids. When a cylinder is subjected to internal pressure, at any point on the cylindrical walls, three types of stresses are induced in it. These three are mutually perpendicular to each other, or they are acting perpendicular planes. These three stresses are, one is hoop stress, it is also called circumference stresses, and the second one is longitudinal stress, and third one is radial stresses. The hoop stress or circumference stresses, these are directed along the tangent to the circumference of the cylinder, having tensile in nature. Thus, due to the effect of hoop stress or circumference stresses, the diameter of the pipe is increases or shell is increases. Longitudinal stress. Here in previous case we have taken hoop stress now. This represents the elevation of the cylinder. These are the stresses which are acting. If it is there in line, that is a tangential to the circumference of the circle, these are acting now. Or it is almost perpendicular to the diameter of the shell now, that is the cross section of the shell. Hence, due to the effect of this one, the diameter of the shell is increases. The second one is longitudinal stress. These stresses are directed along the length of the cylinder. These are also tensile in nature and tend to increase the length of the pipe. The third one is the radial stresses. These are in compressive natures. Its magnitude always is equal to the internal pressure but acting as in opposite directions. Hence, it is having maximum values just inside the cylinder, and the value becomes decreases. Finally, it becomes zero at the outer surface of the wall. There, generally, it is exposed to atmospheric air. Hence, the outside pressure is treated as equal to the atmospheric pressure now. So, in these three types of stresses, first one is known as hoop stress. It is also called circumference stresses. Because of that stress, the diameter of the shell is increases. The second one is we are taking longitudinal stresses. It is also tensile in nature, but the effect of the stress is to increase the length of the cylinder. The third one is the compressive stress, that is acting in opposite directions, in which the pressure inside the cylinder is acting. So it is a compressive nature. Okay, these are the three types of stresses. Generally, the shell is subjected when internal fluid is having certain pressure now. These cylinders generally classified into two types now. Already we discussed, one is a thin cylinder, another one is a thick cylinder. Here the thin and thick cylinders generally classified just based on its thickness only. When the cylinder spherical shape is considered to be thin, when the metal thickness is small as compared to the internal diameter. When if D is representing the internal diameter of the shell and T is representing the thickness of the shell, what it is represented here now. This is treated as here now the diameter. Okay, according to the classifications, here when the thickness of the shell is equal to or less than, here it is equal to or less than 0.05 here D, then the type of shell is called thin shell. If it is a more than 0.05 D, then it is known as a thick shell or thick cylindrical shell now. Here whenever a thin cylindrical shell is subjected to internal pressure, its walls are subjected to the tensile stress. It is because we are taking the failures of shells now. The shells is nothing but here now failures because of the two types now. When the shell is subjected to internal pressure, it's subjected to two types of stresses. Particularly, we are taking thin cylinders now. One is circumferential stress, one more is known as longitudinal stress now. In circumferential stresses, it is always acting the perpendicular to the tangents what are taken to the at the circumference of the circle to its length, or in other words, it's the perpendicular to its diameter. So, because of this effect, it splits into two troughs as shown in figure now. Here it is the one, and one more is here like this now. That is the length of the diameter that decreases because of lateral stress that is inducing, and the diameter increases. The failure occurs only here by splitting into two types now. This stresses when the pressure inside the cylinder when it exceeds the permissible limit, then only is likely to fail. But because of circumferences, it is divided into two troughs or it is divided into splits as shown in figure now. Now the second one is here we are taking longitudinal stress. The longitudinal stress means again it is acting just tensile in nature. Because of this stress, the cylinder is split into two cylinders. Here are two parts as shown in figure now. Okay, these are the two types. Generally, the cylinder fails because when it is subjected to internal pressure of fluid, when that fluid pressure exceeds the permission limits, is likely to split into two types as shown in figure now. So the stresses in the cylindrical shell, thin we are taking now. When a cylindrical shell is subjected to an internal pressure, it was also subjected to two types of stresses. One is known as circumference stresses, the second one is known as longitudinal stresses. The third one, what we have taken earlier now, here no radial, it is there, radial stresses. Generally, this value is negligible in case of thin cylinder, hence we are not at all considering it for thin cylinder. It is only applicable to the thick cylinders now. So, here two types of stresses we are considering in case of thin cylinders. One is known as circumference stress, second one is known as longitudinal stress now. Here first I am considering circumference stress, it is also called hoop stress now. Okay, because of this, here this is known as the cylinder. The pressure is acting internally. So here these are acting almost tangent to the, that is at the circumference to the tangent. Hence these are nothing but here now almost they are splitting into two types as shown in figure now. Here it is here now these are nothing but acting tangentially at the circumferences. Because of this effect, it splits into two types now. We have to calculate what is the maximum stress that can be induced in it before failing now. Let L is representing the length of the shell now, and T is representing the thickness of the shell. P is representing the intensity of the pressure taking. So the total force acting on the diameter is equal to, it is the perpendicular we are taking, because we have to consider this area now, which is the perpendicular to it now. Here it is given, this area we have to take it now, a perpendicular now, which is equal to the diameter of the internal diameter of the shell, but its entire length it is given now. And so here the resisting area is equal to, we can take it as D into T now. So the total force which is acting, it is equal to, we can take it as P into D into T now. So the total force acting here equal to P into D into, sorry, here it is equal to this length of the, because we are taking the length now, length of the cylinder now. Here it is equal to PD L now. Before filling now, that is the pressure what is acting now, the system which is acting because of internal fluid, which is also equal to the resistance force should be, both should be equal now. That is according to Newton's law, the action as well as the reactions both should be equal in magnitude in opposite directions now. And so from this relation we are taking, the circumference in the shell is equal to total force divided by resisting area, which is equal to PDL by divided by resisting area is equal to, here it is nothing but thickness, it is the thickness now. That is the total thickness is equal to 2 into T, but at the entire length is also we have to consider, that is area which is resisting. It is equal to 2T into L now. So from this relation we got to PD by 2T, that is known as the stress that is induced in the thin cylinder when it is subjected to a fluid having pressure is equal to P. But in the case of boilers or the shells, the two ends are joined by welding, or sometimes it is also joined by using the riveting process. At the junction, when comparing with the remaining part, it is having lower strength, hence the efficiency also plays an important. Here N is the representing the efficiency of the joints. Generally it is compared with the original strength of the materials. It is always less than 1 only. When it is expressed in terms of percentage, it should be less than 100%. In that case, the hoop stress is induced in the cylinder is given by PD divided by 2T. 2T is already we calculated in previous relations, but divided by efficiency we have to take it now. Okay, this is the formula generally used to determine the what is the allowable stress. This is before just break into two parts by using which method? Circumferential method now. That is circumference. Circumference is given by sigma c is equal to PD by 2T divided by again efficiency, because we have to consider the efficiency of the joint or the welded part now. Now we are taking the problems based on the relation now. A cylindrical shell of 1.3 meters diameter is made up of 18 mm thickness plates. Find the circumferences in the plates. If the boiler is subjected to the internal pressure of 2.4 megapascal, take efficiency of the joint is equal to 70% now. So the given data in the problem is the diameter of the shell is equal to 1.3 meters. Since here we are taking all the dimensions into millimeters, we are converting it is equal to 1.3 into 10 to the power of 3 mm now. The thickness of the plates is equal to 18 mm. Internal pressure is equal to 2.4 megapascal, which is equal to, we can take it as 2.4 newtons per mm square now. So efficiency of the joint is equal to 70%, which is equal to 0.7. So according to the relation of circumference stress, it is given by sigma c is equal to PD by 2Tn, where PD is representing the pressure inside the cylinder when it is filled with the fluid now, and D is representing the internal diameter, T is representing the thickness of the shell, And substituting these values in this equation we got, which is equal to 32.4 into 1.3 into 10 to the power of 3, here is given now. From this relationship divided by, we required 2t n is required now, which is equal to 2 into 1.8 into 0.7. So from this relationship we got to 124 Newton per mm square, which is equal to 124 megapascal now. Now the longitudinal stresses. These are the stresses acting along the length of the shell as shown in figure now. When the fluid is filled within the cylinder or because of pressure exerted by the fluid inside the cylinder. As a result of this internal pressure, because we are considering that pressure along the lengthwise directions, along the axis of the cylinder, so its tendency, because of this effect, it is having tendency to split into two pieces as shown in figure here now. Here please 1 and 2 as shown in figure now. That is, the pressure is acting along the axial directions. So in order to determine the magnitude of internal resistance which is acting inside the cylinder, let P is representing the P intensity of the fluid pressure, and L is representing the length of the shell, D is representing the diameter of the shell, and T is equal to thickness of the shell we are considering. So the total force along the length the shell is given by, because we have to consider the force along this length, this one now, in this direction. That is, pressure is given P now, fluid pressure, but the area nothing but we have to take the entire area of the inside cylinder, that is the cross section of the cylinder we have to take it, which is equal to how much it is, pi d square by 4. This is nothing but the force that is acting along the axial directions or along the longitudinal directions. But before splitting, that is, internal stresses are developed within the cylinder to resist this force now. So what is it now? Just assume here now, sigma 1 is representing the, that is stress, that is allowable stress within the cylinder now. That is, what is the resisting area? Resisting area nothing but this walls now, because it is splitting only this one now. We can take it as pi d into thickness d now. This is called the resisting force. But the action force, what we have taken? Pi by 4 d square into p we have taken now. Both should be equal in magnitude now. Just before break, that's why we are taken. Both should be equal in magnitude now. So I am equating these two equations we got from this relation now. That is, here now sigma is equal to, here now pi p get cancelled now. What we are having, just we are taking just sigma is equal to p d square by 4. Here d it is there now. Again it cancel now. Here it goes like this now. That is pd by 40. But in the previous case, in circumferences, we got this value is equal to pd by 2t only now. That is the longitudinal stresses that is induced within the cylinder when the same pressure is acting, it is equal to the half of the stress that is induced when we are considering, that is the hoop stress now. Hence, for designing point of view, that the maximum, that is nothing but we have to consider only hoop stress, not the longitudinal stress, because of which stress is having more value, we have to consider it now. So for the design point of view, we have to consider only hoop stress, particularly in the case of thin cylinders. Now taking just a problem 2 now. A gas cylinder of internal diameter 40 mm is 5 mm thick. If the tensile stress in the metal is not exceed to 30 megapascal, find the maximum pressure which can be allowed in the cylinder now. So the given data in the problem is the diameter of the cylinder is given, d is equal to 40 mm, thickness of the plate is equal to 5 mm, and the tensile stress is equal to sigma is equal to 30 megapascal, which is equal to 30 Newton per mm square now. Let P is representing the maximum pressure which can be allowed in the cylinder. the circumference is equal to, we are having PD by 2T, which is equal to sigma C into 2T divided by D. From this relationship we got which is equal to 7.5 megapascal or 7.5 Newton per mm square. This problem is most useful for design of air pressure, that is nothing but how much maximum pressure that can be allowed, or thickness of the materials that should be used for making that particular shell. Hence, for the design criteria, already told, we have to consider only hoop stress now. That's why we have taken P is equal to sigma C here D divided by, that is PD divided by 2T. We have taken these equations. Note that since the circumference is double the longitudinal stress sigma 1, therefore in order to find the maximum pressure given, stress should be taken as only the circumference stress. Now design of thin cylindrical shell. Already we have told just two types of stresses are that are induced in the thin cylinder when it is subjected to a pressure exerted by the fluid. Now let us consider certain parameter for the cylinder. Assume the cell is representing the length of the cylinder. D is equal to diameter. The intensity of maximum internal pressure that should be allowed be P, and circumference pressure is equal to sigma C now. So here design means general the word is how much thickness we have to keep to resist a particular when a pressure of P is allowed inside the cylinder now. So according to our previous discussions, we have to consider only the circumference stresses for designing of thin cylinder. So that equation is given by here now, sigma C is equal to pi D divided by 2T now. So from this relation, here it is equal to PD divided by 2T now. P is nothing but already given for particular pressure, how much thickness that is the required now. Okay, based on this nothing but we have to determine now thickness how much it is. Sigma C is representing the stress, that is the permissible stress. It is just given according to the design data. So sigma C we have to collect. P is nothing but a pressure already given, how much this is nothing but a pressure we are allowing inside the cylinder. So D is nothing but already given, only how much thickness of the shell that should be kept. This is comes under this design of thin cylindrical shell. So the required thickness of the shell is calculated from the relations now. That is the sigma C is equal to PD by 2T. From this relation T is equal to, we can take it as 2 into sigma C divided by pi D now. So we have taken T is equal to 2. Here we have taken these equations now. P D now. So if the thickness so obtained is not round figure now, generally when you are doing the calculations, assume just you got to 8.5 mm. In this case, instead of taking 8.5, better to take in round figure 9 mm. So from this relation, what is the thickness we got it now? Thickness is equal to, this relation is not good. It is equal to pi D divided by here 2 into sigma C. This relation we have to use now. If the thickness obtained from the longitudinal stress will be half of the thickness which is obtained when it is calculated by using circumference stresses, hence it should not be accepted. So for determination of thickness, we have to use only the relations between the circumference stress as well as the pressure, that is allowed now. Okay, based on this relations, we are taking one problem now. A thin cylindrical shell of 400 mm diameter is to be designed for an internal pressure of 2.4 megapascal. Find the suitable thickness of the wall if the allowable circumference is 50 megapascal now. So the given data in the problem is a thin cylindrical shell of 400 mm diameter. That is the diameter of the shell is equal to 400 mm is given. is to be designed for an internal pressure of 2.4 megapascal. That is the pressure that should be allowed. The pressure of the fluid that can be allowed 2.4 megapascal. It is equal to 2.4 Newton per mm square now. Find the suitable thickness. T is equal to, we have to determine now. But the condition is given, the allowable circumferential stress is equal to sigma c is equal to how much it is? 50 megapascal. That is nothing but 50 Newton per mm square we have to take it now. So by using the relations now, thickness of the cell is equal to PD divided by sigma c into T. Because we have taken that relation is equal to how much it is? Sigma c is equal to PD divided by 2T now. T I require now. T is nothing but equal to PD divided by 2 into sigma now. So we have to use these equations now, which is equal to pressure allowed is equal to 2.4 megapascal already given now. So 2.54 and D is equal to 400 is given now, divided by 2 into 50 it is given now, 50 Newton per mm square now. So by using the relations we got 9.6. According to previous discussions, when the value which is obtained, it is a fraction value, just better to take always the round figure just above it now. That is the 9.6 nothing but equal to 10 mm we have to take it now. So based on this one more problem. A cylindrical shell of 500 mm diameter is required to withstand an internal pressure of 4 megapascal. Find the minimum thickness of the shell. If maximum tensile strength of the plate material is 400 megapascal and efficiency of the joint is 65%, to take a factor of safety is equal to 5 now. Here the diameter of the shell is equal to given 500 mm. The internal pressure is given 4 megapascal. 4 megapascal means 4 Newton per mm square. Tensile strength is equal to 400 megapascal. 400 Newton per mm square now. The allowable tensile strength is equal to sigma c is equal to tensile strength divided by factor of safety. That is important now. A factor of safety is equal to given 5 now. Here tensile strength is equal to how much is given? 400 megapascal is given. 400 divided by 5 is equal to, that is 18 Newton per mm square. This is only allowable stress within the cylinder now. And so for design point of view, we have to take these values only for calculation of the thickness of the shell now. So the minimum thickness of the shell is equal to given by PD by 2 into sigma. Here multiplied by the efficiency of the joint is also we have to consider now. From this relation we got to 4 into 500 divided by 2 into 80 into 0.65. From this relation we got to 19.2 mm, that is nothing but equal to 20 mm we have to consider it. Okay, this is to give the just introduction of what is the thin cylinders, that is the difference between the thin cylinder as well as the thick cylinder. So what are the stresses that is induced? We determine this, we observed it is 3 types of stresses that are induced in the cylinder. One is circumferential, second one is longitudinal, third one is radial now. The radial stress that is induced, it is a compressive nature, but in case of thin cylinder, its value is very, very less when comparing with the circumferential. Hence, generally it is neglected in the case of thin cylinders now. So, what is the pressure that is allowed into the cylinder now, particular for thin cylinders? So, based on that one, we calculated the pressure as well as the stresses that are induced now. And sometimes, since the joint is made up of welding or by using the strength, the efficiency of the joint when it is considered, how much pressure that is allowed we determine. The third one is just based on the safety factor we have taken one more now. So by using this information we can design what is the thickness of the shell that is required for the given pressure of the fluid that is allowed now. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.